Hi again. In the last video, if you rewatch it and think about the ideas that we introduced in the last section of it, you will notice that we discussed certain interesting idea that circulation is actually physically is taking care of the flux of vorticity that crosses a given cross-sectional area. Or you can think about it as the closed curve integral of the velocity that is tangent to the closed curve as you go around the closed curve. You can also calculate circulation that way. The idea that was introduced there can be mathematically written in a robust way, and that's what Kelvin's theorem tells us. Kelvin's theorem tells us that if you have a closed curve, which you can show by, for example, a closed curve like C, like this. And if you take fluid elements inside this closed curve and calculate the circulation around this closed curve, which would be velocity v as a vector dotted to ds. So ds, for example, will be element of line like here. So you can actually integrate these around the closed curve, v dotted to ds, and you get the overall circulation around this curve. If you take the closed curve and fluid elements inside it which have a fixed identity and follow those fluid elements and always track this closed curve around them, at each instant of time you can calculate circulation for that and follow that in a Lagrangian manner and calculate the rate of change in that circulation. That's the overall total derivative or the Lagrangian derivative of circulation gamma c with respect to time. If you do that, that can be changed. That can have a rate which is either positive or negative. It can change based on any of these three components or elements, adding or subtracting something to the overall balance of torque around this closed curve. So if you think about it, we are dealing with angular momentum. So this is the rate of change in the overall angular momentum. And anything that can exert torque around this closed curve can change it. You can have certain, as we have discussed before, certain contributions from viscous forces. You can have certain other contributions from body forces or pressure forces. And remember, these are only important around the closed curve that we have drawn. So if you have a certain scenario in which these viscous terms, for example, are unimportant around the closed curve, which is the condition we described in the lecture videos as the so-called inviscid assumption. But again, that doesn't mean flow is inviscid everywhere. It means that viscous contributions are negligible around the closed curve. Or another condition in which body forces are conservative, so that this integral, when you go around the closed curve, becomes equal to 0. Or barotropic flows, where pressure is only, or density can only be a function of pressure, where again helps us to cancel this first term, would give us this result that every term on the right-hand side vanishes, and you will be left with this conclusion that for these three conditions, the change in circulation with time in a Lagrangian manner would be equal to 0. So the total derivative of circulation around the closed curve with respect to time will be equal to 0. And that tells us that the circulation around the closed curve remains constant if we follow that closed curve. We also showed that there is another way of writing the same concept rather than an integral way of demonstrating it. We can also demonstrate it in a differential manner. And that came by taking the curl of the Navier-Stokes equation, and we call this as vorticity equation. So if you remember, we took the curl of Navier-Stokes equation, and that gave us an equation which looks like the total derivative of omega with respect to time, d of omega as a vector over dt, is equal to the sum of two terms. The first term is vorticity omega dotted to grad operator or del acting on velocity. And the second term is nu, which is kinematic viscosity, multiplied to the Laplacian of vorticity as a vector. And again, if you want, recall that nu is defined as dynamic viscosity mu divided by density, which is rho. This equation, which again we call it as vorticity equation, has some interesting meaning too. The overall rate of change of vorticity can happen due to two different terms. One has a viscous nature. Vorticity can diffuse in our domain due to viscous interactions. That's how, when you have a flow next to a wall, the fact that your fluid elements have to follow the no-slip boundary condition, and they will have zero velocity close to the wall, and a little bit above the wall they have a certain velocity that generates vorticity close to the wall, and that vorticity generated close to the wall can diffuse inside into our domain or inside our domain due to viscous interactions. So that's the nature of this physical nature of this term. It's really the diffusion of vorticity due to viscosity. But at the same time, vorticity can change not only due to viscous effects, it can also change due to the geometrical change that we will have in our flow due to geometrical changes in our flow that we have with respect to vortex lines. If the kinematics of the flow makes the vortex lines get elongated, we will have an increase in vorticity. If the kinematics actually goes the opposite, makes the vortex lines become compressed, we will have a decrease in vorticity. And that's very much an idea that we can easily also conclude from the conservation of circulation. For example, the net circulation being equal, the net circulation remaining constant, or the rate of change of the circulation being equal to 0, will give you exactly similar picture that I discussed here. If you have a vortex line and you stretch it, vorticity increases. If you compress it, vorticity decreases. A very good demo and a very good place that these ideas get combined is, for example, flow of a channel around a simple bump. So imagine this blue line that I've drawn here is the free surface height of water, and imagine that water, so let me just make sure that it's thick enough that you can notice it. So this is the blue line that I'm drawing, and imagine that water is entering from left with a certain velocity, and it's going past this bump, and again it goes to a outlet which is having the same cross-sectional area as the inlet, and it goes out from the other side. This flow that I have, if you have seen in the movies and in lecture videos, if I generate a vortex line and a group of vortex lines and connect them together to make a vortex tube, I can draw that tube here. And then I can look at what will happen to this vortex tube as it goes over the bump. Here it has a relatively long, elongated structure. As it reaches here, to conserve mass, since I'm following this vortex tube in a Lagrangian manner, it has to conserve volume, density is constant. So the cylinder has a lower height here, and to conserve volume, it has to become expanded. It has to become wider in area. You can easily think about the amount of vorticity in the first point, omega 1. When you reach here, you have a different amount of vorticity, omega 2. And again, when you come on the other side and pass this bump, you come back again to the same cross-sectional area of the flow that you had. So your vortex tube again comes back to its original height, and it has to elongate back to its initial height, and that means that its cross-sectional area, which was increased here, has to again be decreased to a smaller cross-sectional area. So you can think of a cylinder that comes to here and gets compressed, and then again gets elongated. If you use conservation of vorticity, which tells us that d gamma c over dt should be equal to 0, and combine that with conservation of mass, which tells us the overall mass of this vortex tube, d mass over dt, should be equal to 0. So if we use these two conditions, we actually can reach an interesting conclusion. The conservation of mass tells us that the cross-sectional area has to increase. The vortex tube becomes wider, and then as we reach the top of the bump, and then again decrease as we go around it. And with the fact that circulation is basically, in this problem, omega times, if this element of vortex tube we have chosen is infinitesimally small, it's basically omega or vorticity multiplied to the area of the element we have chosen, which is dA. And the fact that dA at 1, dA at 2, and dA at 3 have a certain relationship with respect to each other, we can write it down. So dA at 2 is much larger than dA at 1, which is equal to dA at 3. So that's the relationship we have between cross-sectional area of these vortex tubes. This simply comes from conservation of mass. And when we combine that with conservation of vorticity, which is the circulation should remain constant, tells us that now that the cross-sectional area is increasing, vorticity has to decrease as we compress vortex tubes. So omega 2 would be smaller than omega 1, which should be equal to omega 3. So that's the conclusion we get. And that was the demonstration that you have seen in Asher Shapiro movies. If you take a ping pong ball and put it on the surface of this vortex tube, it is spinning relatively fast here. As it reaches the peak of the bump, it spins slower. And as you pass the bump, it starts to again accelerate in the spin rate. And at this point, it spins exactly as fast as you had as the other side. And this is exactly the analog to figure skater. When you spin and close your hands, you are here. When you reach here and open your hands, you spin slower and you are here. Again, if you close your hands, you come here and spin exactly with the same rate that you had initially. Of course, in real problems, there is viscous dissipation, and you will never obtain the same spin rate because some of that angular momentum has been dissipated due to viscous interactions. But as a general rule, you can clearly see that whether you use Kelvin's theorem, which can be written in terms of conservation of circulation, or if it's not conserved due to one of these three elements that can be present in our flow field, and the other path that you can go forward in these problems, which is the vorticity equation, whether you use either of them, the final result will be something similar. And the final result should be always consistent with the idea of conservation of angular momentum when there is no external overall torque acting on our system. This would be the review that we wanted to do on the topic of vorticity and circulation. If you notice, we talked about dissipation of vorticity into our domain due to viscous effects, especially when you are close to a wall. And that's the idea that we have no slip boundary condition. And the flow field will get affected by that. That is the topic of boundary layer and boundary layer theory, and that would be the topic that we will do a short review of it in the next video.